Hi, everybody of Physics 2. The purpose of this presentation is to give you an idea of what we will be doing next. I know we covered so far optics, we covered also the electric field, we covered the electric potential, we covered also circuits and so on and so forth. As the circuits, we did just the resistors and capacitors at this point. We had 3 exams, we still have to do at least for 2 more exams, and plus the final, of course. And now, since the instruction is moved online, so I'm giving you an idea of what to look for in the next few days when we meet. We will be meeting online, of course, on Canvas, and I already set up the times when we meet, but there will be some recordings that I'd like you to also follow. So this is basically what we'll be seeing in Chapter 27. Chapter 27, we will learn the Lorentz force, basically, that gives me the force a particle moving with a velocity v inside a magnetic field B experiences. We'll define the magnetic field. We'll go a little bit of the types of magnets that we encounter. There are basically 2 of them. There are permanent magnets and also electromagnets. This force, of course, this is the magnetic force that a particle will be subject to. I dressed it up with the symbol B. Of course, from this is the cross product, and of course, one of the properties of the cross product. This product is the force itself is going to be perpendicular both to velocity and perpendicular also to the magnetic field, and it's given by the right-hand rule. If you don't know what the right-hand rule is, it's basically like the one we know about the different axes, like the Cartesian coordinate system, x, y, and z. This is a right-hand coordinate system. So think about this one as being the velocity v. This would be the magnetic field v. The cross product of v cross b is, of course, going to be the force F. Now, note, you don't have to have a 90-degree angle in here. This could be any angle you wish. So actually, the magnitude of the force is going to be simply equal to QV, and sine of the angle that is sustained between V and B. We will go in more detail when we cover this material, so I don't expect you guys to know all of this things at once, but just to give you an introduction of what to expect, at least, so that you have a rough idea of what to do. We'll apply this force, we'll try to understand how this force works, and so on and so forth. The other thing that we're going to cover in this chapter is, of course, the magnetic flux. The magnetic flux is defined just like we did when we defined it for the electric flux, and it's just the dot product of the magnetic field with the area summed over the entire area. I mean, this one to be a vector and mean for it to be like that. So so you have an area of some sort, can be open or closed, and we will see the case of the closed area very quickly, and we'll understand why. So you have a magnetic field, and here you have an area. This is dA, the element dA. This is, of course, the magnetic field. I took it uniform. It doesn't have to be. The cross product is basically formed by multiplying the area and dot product with the magnetic field, and from there we're going to get the flux when we sum through this entire area that we're taking in this case. Now, this is a special case. This is the equivalent of Gauss's law for the magnetic field. The flux of a magnetic field over a closed surface, so this is what that stands for, is equal to 0. And there is a reason for that, because magnetic dipoles do not exist. All dipoles in magnetic monopoles, I should say, do not exist, and magnetic field exists only in the form of dipoles. In other words, you can only find the North Pole by itself, and you cannot find the North Pole by itself and the South Pole by itself. You find them as part of one thing, and that's what that expression is saying. Basically, no monopoles. Unlike the case of the electric field, where that integral amounted to the distribution of the charge, I mean the charge enclosed divided by some constants. In that case, it was epsilon naught. And because you can isolate the electrical charge, because you cannot isolate the magnetic charge or the magnetic poles, basically you have them always as a dipole, north and south together, or a magnet. Another expression we're going to learn in this chapter is for a wire that is carrying the current I in it inside a magnetic field of length L. So the wire has a specific length, is subject to a force when it's inside a magnetic field given by this expression. Again, it derives from that one from Lorentz force, so you can see exactly how that comes to be. But again, this is a wire in here. So let me get my drawing tool in here. I'm going to change the color a little bit. So this is basically a wire in here. Then you have a magnetic field somewhere in here. So this is B. And the wire has a current I running through it. So the wire is going to be experience force. Again, that force is going to be perpendicular both to the electric field and the wire itself that has a current running through it. And the direction of the wire itself has to go in the same direction where the current is flowing. So it has segment L, and I can find exactly how much force there is in that. There will be a lot of applications in here for this law. We're going to find also something else similar to what we did when. Let me change the color back to green because I like that color a little better. So we're gonna also learn about the dipole moment. And the dipole moment is when you have a magnetic field, when you have a magnet inside the magnetic field, basically is going to be subject to a torque. That torque is given by the expression mu, where mu is actually the dipole moment, similar to what we did when we did the electrical dipole, except in that case it was the electrical dipole that entered the expression. The energy of the system then is going to be given similarly to the dot product of the magnetic dipole times the magnetic field, with a minus in there indicating that you have a magnetic dipole. That magnetic dipole would want to align itself with the magnetic field, and this is the basis for basically a lot of applications, including of course motors. I don't know if we'll have time or not to cover the whole effect, but if we do, we're going to introduce that. This is chapter 27, basically, all the topics in chapter 27. In chapter 28, we're going to discover an interesting law called the Newton-Savart law. Basically, that's the question we're going to answer in that chapter is, what is a magnetic field? Where is it coming from? It turns out that it is given by the electric field, just as much as when we learned in the case of electricity that charges produce electric fields. In this case, actually, it's electric currents that produce magnetic fields. So this is the expression. It's a little bit nastier than what we did in before. Oops, this is the unit vector. That's where I put the hat in here, divided by the distance squared. So what I have in here, I have a segment of a wire that has a current I running through it, and a distance r from that wire. Magnetic field can be measured in here. So the segment is of a small length dl. So this is, let me try to draw it in here. I know we are going to cover this material in detail, but just to give you an idea basically of what we're doing, so I'm going to give you that. So I have an element in here, dl. It has that current that is running through it. Now, the distance r from it, we're going to have a magnetic field, and the magnetic field is going to be not in the direction like when we did for the electric field, but rather in a direction perpendicular to the unit vector in here, r hat, and the element dl in this case. Expression is a little bit nastier, and it's actually the magnetic field is also proportional to 1 over the distance squared, so this distance squared. But also a property in here that is property of the medium where this thing is where the entire measurements are happening, and that is expressed by the value mu naught. Remember when we did electrostatics, we had 1 over 4 pi epsilon naught. In this case, instead of dividing by epsilon naught, we're going to be multiplying by actually mu naught. So in our case before, epsilon naught lived in the downstairs. Now we're going to see mu naught, the equivalent for that expresses basically the properties of the medium. It's called permeability of the medium, and it's going to be living upstairs. We're going to use this expression to find the magnetic field produced by a wire at a distance r from it that has a current, uniform current running through it, and the expression will turn out to be just mu naught I, where the I is the current running through this wire, divided by 2 pi times r, where r is the distance away from it. We'll have some more applications than this. And then we're going to discover a very, very important law in chapter 28, and that law is called Ampere's law. Ampere's law basically is going to allow us to calculate the magnetic field. The circulation, this is not a double integral, this is a line integral of the magnetic field over a closed path. So if I have a closed path in here, and I want to find this integral is through the closed path, of course we're going to take some cases in here and see how that works, is equal to mu naught times I enclosed. This is similar to Gauss's law, except this is this law works for the magnetic field, and this is not a double integral. This is not the calculation of the flux of the magnetic field. Again, the flux of the magnetic field over a closed surface. We just saw that it has to be zero. This is the circulation of the magnetic field over a closed path is going to be equal to mu naught times I enclosed. This I enclosed is an algebraic expression. We're going to take a convention that if the currents are coming out of the surface, that is enclosed by this path. So this is actually a path integral, just to emphasize this point in here, and this is the path we're doing the integral over. So if I have a current that is coming out, it's going to be taken positive. The current that is going in is going to be taken negative. So I do the sum of these currents that are enclosed by this path, and that is going to give me the circulation of that magnetic field. Again, the value of mu naught lives upstairs, just to give it a comparison to Ampere's law, where we had the charge enclosed divided by epsilon naught. In this case, it's multiplying by mu naught. And we'll go into details about this one, and this is going to be a powerful law that's going to help us understand how to calculate the magnetic field for different areas. Once we move to chapter 29, this is again down the road, so this is the third chapter in this group of chapters. We're going to just talk about the Faraday's law. And Faraday's law basically gives us something. Remember what the EMF is. We discussed that when we were talking about the circuits. So the EMF can be produced by a changing magnetic field. So if I have a magnetic field and calculate its flux, as I defined it upstairs, and find the rate at which the magnetic field is changing, this gives me the magnitude of the EMF. Electromotive force would be generated. And the minus sign is due to Mr. Lenz, and Mr. Lenz basically expression says that this EMF is so that it opposes the change in the flux of the magnetic field. Let me go back a little bit in here and talk about this law. This is Faraday's law again. Mr. Faraday was thinking that, look, in this Ampere's law, basically, what I have in here, where is Ampere's law? Yeah, this Ampere's law basically is just above it. In Ampere's law, what I have actually, I have an electric current producing a magnetic field. Remember, electric currents, they're due to electric fields. So when you have an electric field between the ends of a wire, I have an electric current. That electric current turned out by Ampere's law to produce a magnetic field. Mr. Faraday thought maybe the process backward would work. Can a magnetic field produce an electric field? Because this EMF is just basically like a battery now. So it's going to run currents through a wire. So it turns out, after doing the experiments, that it's not the magnetic field that does produce that, but it's a changing magnetic field. As a matter of fact, it's flux. So if I have a region where the magnetic field, I have more and more field lines are coming, and I have enclosed that region by a wire, so this is a conductor, then I will see, of course, the current will flow in such a way to decrease. If the number of field lines is increasing this way, there will be a current flowing this way through this wire that produces, per Mr. Ampere's law, a magnetic field that opposes the increase in the field lines in that region. And that's where the minus sign is coming. The minus sign is going to give me actually the direction over which the current is going to flow. This is important because this is actually the principle with which we have current generators. And when you go to Hoover Dam, that's exactly what they do. They have magnets and they run turbines, and those turbines have go around, and as they turn inside a magnetic field, they produce currents, and that's how we get currents in our houses. And that's actually the principle also of different generators that you can use for current, whether they are powered by falling water in a waterfall or by gas engines. Anyway, So we do a lot of applications. Again, the EMF is going to be defined as being the circulation of the current inside the electric field in a closed path, of course, through the wire itself. So this is going to be the EMF, and from there we do a lot of applications. And of course, we're going to conclude this chapter by a remark that Maxwell actually noted that there is a flaw in Mr. Faraday's law, in Ampere's law, and that flaw has to do with the fact that we'll discuss exactly where the problem is going to arise, and he had to introduce, basically based on a thought experiment, and later on he was right. Actually, he believed that there is something called conduction current. What is it? I forgot the name for it right now, but he introduced a new term in such a way that actually the circulation of the magnetic field, not as given by Mr. Ampere, because that part is from Mr. Ampere, plus a new correction in here that has to do with the fact that if I have an electric field that changes, its flux will change in the region, and that will induce a current, and that current that is going to be there, that also can produce a magnetic field, and that is going to close the whole path, the whole circle, and then we will have all of Maxwell's equations ready for chapter 30 and beyond. I hope this is just an introduction. This is not intended to be a full lecture. So to give you an idea of what to look for in the next 3 chapters, as a matter of fact, some of the applications later on are going to be dealing with AC circuits and inductors and inductions and things like that. That's going to be dealt with in later chapters. Again, if you have any questions, please do not ask them on YouTube. Ask them directly on Canvas. Thank you.